Hello, everybody. Just tell me in the chat section if we are live or not. Okay, we are live. If there is anybody in the chat section, please let me know. Am I audible and visible to all of you? Just give me a quick thumbs up in the chat section so that I'll know everything is fine with my stream. Just give me a quick thumbs up in the chat section. If everything is fine with my stream, guys, please just give me a quick thumbs up so that we can start today's session. And in today's session, we are going to discuss discrete mathematics complete revision for IIIT Hyderabad, IIIT Hyderabad for the exam PGEE. Okay, I think everything is fine with my stream. If at any point of time, if you face any kind of issue, just let me know in the chat section. Okay, so in today's session, we are going to discuss discrete mathematics complete revision. So basically, we know that discrete mathematics comprises of propositional and their first order logic. Second thing is graph theory. These two are very important. And the third one is set theory. Set theory. And the fourth part here is combinatorics, right? We have four parts in discrete mathematics. So basically, all students are good in set theory and combinatorics. Especially students face problems in propositional and their first order logic and graph theory. So we are going to revise complete propositional and their first order logic and graph theory in today's session. So please share this session with any of your friend who is preparing for IIIT Hyderabad PGEE exam, because this session will be important and we are going to revise all the concepts so that it will give you a heads up in exam. Okay. Uh, Good evening, Yashwant Kumar. Okay, marker शो नहीं हो रहा है. Let me check once. Just let me know if it is fine. Now it's showing or not. Guys, just give me a minute. Let me check why we are facing this issue, and I'll start the stream. क्या हो रहा है यार ये? Just let me know if is it visible to you now? Just let me know if everything is fine with my stream. Now, is it visible? I hope now written part is also visible to you if I'll write prepositions here. Okay. Uh, okay, now it's fine. Okay, so Yashwant is Deepak is asking, is this also helpful for GATE? Yeah, basically discrete mathematics for Triple IT Hyderabad uh, and GATE exam is same, syllabus is same. So we are going to revise in this session. If you want to go in detail discrete mathematics, you find the playlist uh, in the in the playlist section in on our channel, and you will get all the videos. You can learn from those videos. We are going to revise complete syllabus in this session, so if you want to revise, then yeah, this video is helpful. So basically, I told you that we have four subjects in discrete mathematics: propositional and their first order logic, and the second one is set theory, third one is graph theory, and fourth one is combinatorics. Basically, set theory and combinatorics you might find easy, right? The main difficulty you guys will have in propositional and their first order logic and graph theory. So uh, we are going to discuss all of these things in this video. So first of all, you just have to understand what is proposition before starting anything. So basically, proposition is a basic building block of logic, right? Basically, if I have to give any logic behind any statement or anything, that is a proposition. So for proposition, as it is a declarative sentence, so truth value means either the statement is true or it is false. Like if I am saying the sun rises in east and sets in west, so that means either it is true or it is false. Or I'll say that 2 is an even number. Either it is true or it is false. Right? I don't have any possibilities that I can give either true or false to this statement. Or if I'll say that what time is it? What time is it? Is it a propositional statement? No, because I can't assign any truth value. That means I can't assign. Okay, I hope now it's fine. I don't know why we are having so much issues today. Okay, so let's move forward. The truth value of a proposition is either true if it is a true statement and false if it is a false statement. Right? So if I have an argument or a sentence or a statement, if either we have a truth value true for that statement, I'll say that statement is true, and otherwise it is false, right? So propositions have two values, either true or false. Okay, so that is our single proposition, like 2 is an even number, or I'll say 3 is an odd number. So these are my single proposition because I am only saying about one thing, right? But if I'll see here, if I'll combine two propositions, two or more proposition, that will become a compound propositions, right? Like if I'll say 2 is an even number, 2 is an even number, and 3 is an odd number. So basically we have combined two sentences, two statements or two propositions, so that will become compound proposition. So if I'll use this and is basically work as connective. So to join two single proposition, two or more single proposition, we use connective, either it is and or implication. We'll discuss all those things. So this is basically connective, right? So we join two or more compound proposition using connective. So like this, 1 plus 1 is equals to 2 and all birds can fly. We have two propositions here and we have combined these two propositions using and the next one is B is a vowel or E is a vowel. So we have combined this using proposition or, right? Okay, so connectives. Basically, connectives are the words and phrases used to form compound prepositions, right? We use connectives to form compound preposition. We have five basic connectives. First is negation, conjunction, disjunction, conditional, and biconditional. So let's see what is negation. So if I have any proposition and I'll take a negation of a statement, like if I'll say that 2 is an even number, if I have to take a negation, so that means 2 is not an even number. And if I'll say truth value of 2 is an even number is true, but 2 is not an even number. The truth value of 2 is not an even number is false, right? So that is negation. If I'll see here, if we have P as a proposition, it has truth value true, then negation of P has truth value false, and if P has false, then negation of P has truth value true, right? Okay. So the next thing we have is conjunction. So for any two proposition P and Q, their conjunction is denoted by P and Q, which means P and Q, right? This is basically a connective which says and we have disjunction which says or. So if I'll talk about the truth value, if I have two propositions P and Q, if P is true, Q is true, then this statement is true. Otherwise, it will be false in every case. And for P or Q, if P is true, if P is false and Q is false, if both are false, then I'll get a false. Otherwise, I'll get a true in every case, because that means and is working, right? P and Q. So P and Q both should be true, then we'll get the compound proposition true, right? If I'll see the truth value here, truth table here for P and Q, true, 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 false, 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 true, false, 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 false. And if in the same case, if I'll talk about P or Q, that will give me false when both the propositions are false. Otherwise, it will provide me true, right? Just let me know, guys, if you feel any kind of confusion in this topic, right? Okay, so the next thing is implication. So basically for any two proposition P and Q, the statement if P then Q is called implication, right? We know that. If P matlab P is a premises, Q is a conclusion. So if P is happening, then Q should be happening, right? If P is true, then Q should be true. So I can write this statement is if P then Q, if P comma Q, either if P comma Q or if P and Q, right? Q if P, Q when P, Q whenever P, P only if Q. You just have to remember all these terms, because it might happen that in question they ask Q when P. Then you cannot write Q imply P. That will be wrong, right? That is Q when P means meaning is Q when P for P implication Q, right? In this implication, P imply Q, P is called the hypothesis, antecedent or premises, Q is called conclusion or consequence. In this case, just remember if P is true, Q never be false. If P is true, Q is false, I'll get a false, otherwise I'll get a true in all cases. Because what it's saying that if P is true, if P is happening, then Q should also be happening. If P, then Q. But if we get a case that P is true, Q is not happening, P is happening, Q is not happening, that means this will give me a false, right? So that means P is true, Q is false, give me false, otherwise in all cases I'll get a true, right? If I'll talk about the truth table, this will be the truth table. I'll get only false in one case when P is true and Q is false, right? Just let me know if anybody have any confusion in this, right? These are the connectives. Next connective we have is biconditional or double implication. It's basically P if and only if Q, right? If P is true, Q is true, then the statement is true. If P is false, Q is false, then it is true. If P is true, Q is false, then it is false. So what is happening here? Both statements are true at the same time, both statements are false at the same time, then I'll get a true as their truth value. Otherwise, I'll get a false, right? Just let me know if anybody have any confusion, and we can check using truth table that its truth value P, if and only if Q has truth value same as P imply Q and Q imply P, right? Okay, so you can check this truth table and you can easily find out all the truth values. You should be comfortable in applying all the connectives, right? You should remember where to use which connective, right? If I am taking and, that means I have to use conjunction. If I'm using or, then I have to use disjunction. You just have to remember everything. And the most important thing here is implication, right? If P imply Q, then P implication Q. If P comma Q, then also P imply Q. So you just have to remember all these implications. Okay, so next statement is special conditional statement. So basically we have three types of special conditional statement. First is converse of the proposition. Converse of the proposition. So converse of any proposition, P implication Q is Q implication P. Right? Truth value are different. Right? This is basically a converse. Right? If somebody asks me what is the converse of any statement, I'll say if it is a P implication Q, I'll say Q implication P. Right? Contrapositive is P implication Q, negation of Q, implication negation of P. That means I'll negate both the statements and take a and change their positions. Okay, inverse of the proposition is P implication Q is negation of P, implication negation of Q, right? That is the inverse of a proposition. That means we have to negate the proposition P and Q and do not change their position. Like there are some questions like if they ask that find the truth value of the contrapositive of that statement, then first you have to find out the contrapositive, then you have to work for the truth value, right? So it is important that you know how to find converse, contrapositive and inverse. Okay, okay, so and you can remember all these things using this table and that would be helpful, right? The next thing is this is a truth table and you can simply draw the truth table of you can simply draw the truth table of these special conditional statement. But the one thing to here notice is it's our main statement and it is what, it's contrapositive and it's what, converse, and it's what, inverse. If I'll see the truth value of contrapositive and the statement and the argument is same, right? And truth value of converse and inverse is same. So can I say that truth I can say that truth value of its inverse is same as truth value of its converse, and contrapositive की statement किससे truth value match कर रही है, statement से. So what can I say that we'll discuss logical equivalence in the next slide, in which we know that two statements are equivalent if they have same truth values. So here I can say that P implication Q is equivalent. This is a sign of equivalence, that is equivalent to negation of Q imply negation of P. Similarly, I can say that Q implication P converse is equivalent to inverse, that is negation of P implication negation of Q, right? Okay, so let's move forward. There are three types of proposition when classified according to their truth values. So there are three types of proposition: tautology, contradiction and contingency. So what is tautology? A proposition, if it is always true, then I'll say that it is a tautology. Contradiction, a proposition which is always false, right? Let's suppose if I'll take P or Q, right? Okay, let's take P or P, right? If I'll take P as true and P as false, P or P is true is always true. Okay, let's take P or negation P, right? Negation P of is false and negation P is true. If I'll take P or negation P, it is always true. So I can say that P or negation P is tautology. And if I'll take P and negation P, right? If I'll take P and negation P, true and false, then I'll say that P or negation P is false. If I'll take P or negation P, it is always true. So I can say that P or negation P is tautology. And if I'll take P and negation P, right? If I'll take P and negation P, true and false, then I'll say that P or negation P is true is always false. False and true is always false. So I can say that P and negation P is contradiction. And what is tautology? P or negation P is a tautology. And contingency, proposition that is neither a tautology nor a contradiction is called contingency. If I'll take negation P, false, true, I'm getting false here and I'm getting also true here. So that means I'm getting both the values. So I cannot consider this statement as tautology or contradiction. So what will this statement will become? This statement will become contingency, right? Okay, just let me know if you guys have any confusion in this. Okay, if it is fine, just give me a thumbs up so that I'll know you guys are not facing any type of confusion and I'll move forward. Right? We have to move forward quickly because we have a lot to cover in this session. Okay, so the next here we have a question. It says that proposition is a tautology, contradiction, contingency, absurdity. So I can simply find out the proposition, tautology, contradiction, contingency, and absurdity by finding the truth value. I know that. Let's do that. If I'll have a statement P and Q, let's take P implication Q and Q implication P, right? And I'll at the end I'll add them. P implication Q and Q implication P, right? So what are the cases for P and Q? True, 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 false, false, true, and false, false, right? These are the cases. P implication Q is true, P implication Q is false, true, and true. For Q implication P, true, true, false, true. And if I'll take and for both the statement, what would I get? True, false, false, true. So I can see that this is not a tautology because at the end I am not getting all the truth values as true. It is not a contradiction because I am getting the statement as false and true both, right? All the truth values are not false. So we know that if it is not a tautology nor a contradiction, it is a contingency, right? So here option D is correct. Okay, so here option D is correct. Okay, so let's move forward. Okay, so I told you about propositional equivalence. If two statements have same truth value, then it is a propositional equivalence. But it is very difficult for us to define every time that to find out the truth value, because let's suppose if in a statement we have four or five arguments, P, Q, or five or four single proposition, then it would be difficult for us to find out the propositional equivalence. So we have some rules, so we'll discuss them. So we know that what is logical equivalence. So we have some established laws that will help me to prove that two statements, two propositions are logically equivalent or not. First is identity law. That is basic because if P and true, if you will do P and true, you will always get a P, because if P is true, true and true, true. If P is false, false and true, you will get a false. Right? Similarly for P or F. So these are identity laws. Next we have is domination laws. P and F gives you false because if you will take P anything for, if you will take and with false, you will always get a false. Similarly, if you will take or with true, you will always get a true. That is a domination laws. And the next one is idempotent laws. Idempotent, P and P always gives me P. P or P always gives me P. Right. The next one is double negation. Yeah, that is you have to remember because this is important, that negation of negation P is equals to P, right? The next thing is commutative law. Either you will do P and Q or Q and P. Both have same truth values. Similarly, P or Q or Q or P, both will. Similarly, you have associative laws for logical equivalence. This means that the left hand side, this left side has same truth value as right side. So if in question it is required to prove that they have same truth value, I'll directly use associative law. I'll not go for truth table and all that, because we know that it is very difficult to draw every time the truth table, right? So what we'll do, we'll use these laws, right? So these are some pre-established laws. And the next thing is distributive law. Okay, so these are important, but we have some rules of inference which are also going to help us to prove logical equivalence. right? Here we have this important law, which is P implication Q is equivalent to negation of P or Q, right? If you will check the truth value of P implication Q, it will be equivalent to negation of P or Q. Just remember this implication law, and this will be helpful in proving logical equivalence later. Okay. Next thing, De Morgan's law, right? That is also important. It says that if I have, you all have studied De Morgan's law in probability and all. What it do? It takes negative inside, negation of P, and it converts and into or, right? In probability or in set theory, it converts union into intersection, right? Just simply convert and into or and take the negation on both the proposition, right? This is the way to remember De Morgan's law. Again, negation of P or Q, it will give me negation of P and negation Q. I'll take negation on both the proposition, and I'll convert or into and. Like that is De Morgan's law. And you can simply prove it by using truth table. I do not find there is need to discuss this truth table with you. Just let me know if you are fine with this, and you will solve it by yourself. Okay, so that is basically the rules, pre-established rule. But there are more important rules, which are rules of inference, which will be more helpful because these laws are important. For the important laws in this are De Morgan's law, and the next is implication, and the third one is double negation law. These three laws are very important. Just remember these three laws, and you are good to go with questions, right? Okay, so next thing we have is rules of inference. So basically, you have to understand what are rules of inference. In this, we have in pre-established laws, which we have discussed before in previous slides. What we have discussed that if I'll take two propositions, I'll get them either equivalent or not. But what happens? Rules of inference. It says that if we have premises, if we have number of premises, then I can conclude from these premises C, right? Or I can say that if these premises are true, then this conclusion is always true, right? So what it is giving us that if we have number of premises, I'll get a conclusion. So basically we know that what is premise, what is conclusion. If P then Q वाला case है. If P then Q, don't get confused, right? If P then Q, and we know that when it will be false, it will be false when P is true and Q is false. So there is no possibility. So if we have to check the truth value, right? If we have to check that it is true or not, I'll take P imply Q, and if it is false, then it is not true. Otherwise it will be true. Okay, so Aman Rahman is asking what is the difficulty level of PGEE, please tell. Okay, so Aman, if I'll talk about the difficulty level is not so high, but you have to compete with so many students. And I think there are 100 of seats available, right? There are only 100 seats available. So there is a lot of competition because students who have prepared lot for GATE wants to get, if they do not get into good rank in GATE exam, they didn't get the good rank in GATE exam, they want to go for another good colleges. And we know that IIIT Hyderabad is one of them. It has a very good placement. So the competition is high. You just have to be focused while you are giving the exam, because you do not have to do silly mistakes, right? Because what happens when you are under pressure, then you made silly mistakes and do questions wrong, which you can solve it easily. So be focused. Difficulty level is not so high. If you will if you have prepared for GATE exam, then you can easily score good marks in PGEE. But the most important thing is that you have to be focused. And one of the most important thing here is that there is no negative marking, right? That will be helpful for you. Okay, so that is basically rules of inference. Let's move forward. Okay, so the next thing is structure of an argument. So I told you, if we have one premise, then I'll say that premise implies conclusion. But if we have number of premises, P1 implication, so I'll take P1 and P2 and Pn implication Q, because all premises has to be true to imply conclusion. So I'll take here and P1 and P2 and Pn implication Q, right? Okay, so I can say that, and this argument is valid if it is a tautology. This statement is tautology because I know that if it is true, it is false, it will give me false. Then it is not a tautology and it is not valid. I know that it is not valid if I'll get premises true, conclusion false, because I am finding conclusion from all the premises. Okay, so we have some rules of inference that is helpful. It says that if we have P and P implication Q, I'll get a Q. If we have negation of Q and P implication Q, that is, I'll get negation of P. So if we have any question to prove, to find out the conclusion from the statements, I can use these rules of inference. So this is basically modus ponens, this is basically modus tollens, and this is hypothetical syllogism. If P imply Q, Q imply R, P implication R. That is basically a transitivity rule, right? The next thing is disjunctive syllogism. If we have negation of P and P or Q, that means P is not happening and the second statement is either P or Q. If P is not happening, then what happened? Q, right? The only choice here is Q. So I'll get a Q, right? Okay, and the next thing is addition. If we have any statement, if we have any argument or proposition, I can add any another proposition to it. I can write P or Q, right? Exportation is P and Q implication R. I can write it as P implication, Q implication R, right? Next thing is resolution. P or Q, negation of P or R. Let's suppose that P and P, negation P get cancelled, you are left with Q or R. You can remember resolution as this, right? Okay, so these are the rules you can use to find out the conclusion, right? There are many questions in gate exam. You can practice by going on our GFG website. You will get all the questions there and you can practice and you can get good in these questions, right? So the next thing is predicate logic. So what happens, like if I am talking about even number, so I have to work on every even number, like 2 is an even number, 3 is an even number, 4 is an even number. So I can work on that 2 is an even number, it is true. 3 is an even number, that is false. So what happens? Predicate logic help us to compile all the things in between in a statement, in an argument. Like if I'll say that x is an even number. So x can vary, x can be any natural number, right? X can be any natural number. So that is basically predicate logic where we would not be able to find out the truth value unless we specify the value of x. If I'll specify x is equals to 4, then I can say that what is the truth value. But if I do not put the value of x, I am unable to find out the truth value. So that is basically our predicate logic. So if I'll say that predicates are the statement involving variable which are neither true. Okay, so okay, so in the next thing we have is example, like x is an even number. It is an open statement. If I'll put the values of x, I'll get a truth value of each of the proposition. And once we put the value of x, I'll get the proposition, right? If I'll put x is equals to 4, 4 is an even number. It is basically our proposition, right? Right now it is an open statement, but when I put the value of x, it will become proposition, right? Okay, 5 is an even number, 6 is an even number, right? These are the examples. Okay, so in predicate logic, statement is divided into two parts, subject and predicate. This is subject, or I can say that it is a predicate variable, is an even number, and I can denote this by the notation P of x, right? So that means x is true for P. That means x is an even number. I read this. So if I'll say this, it is basically our is an even number and x is our subject, or I'll say predicate variable. Okay. Okay, so in predicate we have some quantifiers, because again we want to work on the truth value of the predicate, right? I want that if I do not specify the value of x, would I get the truth value of the statement, right? Let's see some example. Let's suppose if we have a statement that x plus 2 is greater than x, right? Px is a statement that x plus 2 is greater than x. Let's put x is equals to 1, 2 and 3, right? If I'll put x is equals to 1, 2 and 3, I'll get all the statement true, and I can simply check that from this statement for every value of x this statement is true. So I can say that px is true for all values of x, right? And similarly, if I'll take x is greater than 10, right? Px is a statement where x is greater than 10. It has a value 5. P5, if I'll take 5, 5 greater than 10, it is false, but I'll take 11, that will be true. So if I'll see here, I get two statements, that for the statement in which every truth value is true, and the second statement I have is that one is false, some is false, some is true. So I'll define according to that universal and the existential quantifier, right? Okay, so basically universal quantification is universal quantifiers are the quantifiers in which truth value for all the values is true, all the argument is true, right? All the propositions is true. So if I say that px for all values of x in domain, right? So I can denote it as for all x. If you have studied this symbol in math, this is basically our for all x px, right? So p is x is true for all x for p, right? Px for all values of x in the domain, right? So if I'll take that x, okay, let's take we have taken one example that x plus 2 is greater than x, right? It is true for every values of x. So I can write it as for all x, x plus 2 is greater than x, right? Just let me know guys if you have any confusion, or just give me a thumbs up if everything is fine. And if you like the session, please, if you are learning from this session, just like the session before moving on. Okay, so let's move forward. Next is existential quantifiers. Existential quantification means that there exists at least one value for which px is true, right? There exists at least one x in the domain such that px is true. So I can say that for some x px, we have taken one condition that x is greater than 10. If I'll take 11, 12, 13, 14, I'll get this statement true, but if I'll have 5, then the statement is false. So that means there are some values. There are some values for which this statement is true. So I can write it as there exists x such that x is greater than 10. Right? That is basically our existential quantification definition. Okay. So that means we'll get either we get at least we get 1, 2, 3. There may be a possibility that I'll get infinite. Right? In this, I'll get infinite number of values for which this is true, but I'll use existential quantification. I cannot use universal quantification, because for universal quantification there does not exist any value such that this statement is false. But this statement is false for 5, 4, 3, 6, like these type of number, it would be false. So I can write it as there exists x, x is greater than 10. Okay, and there exists is called existential quantifier. Okay, so we have one question. It is from GATE CS 2012. It says that some real numbers are rational. So anybody from the chat section can tell me what will be the translation for this statement. It says that some real numbers are rational. So we know that because we are using some, so that means we are going to use there exists x, right? So we have to choose out of option A, C and D. B is not true. So anybody from the chat section can tell me which one is true. Okay, anybody from the chat section? Guys, give me a response in the chat section so that I'll know that you are learning from this session, uh, and we'll move forward this session. Okay, so I can see that some real numbers are rational. So if I'll see option 8 says that there exists x such that x is either real or rational, right? But it is not saying that. So option A is also not true. If I'll see option D, so it says that there exists x such that we have x is rational, then x is real. So that means it's saying that x is real, then x is rational, then x is real, right? It is true, but this statement is not saying this, right? This statement is saying that some real numbers are rational. So here if I'll see, option C is correct because there exists x such that x is real and x is rational. So that means we have some x which are real and rational both, right? Just let me know guys if you have any confusion in this question, because that is easy, right? You have to you will going to encounter these type of questions in your exam. Okay, so let's move forward. Next thing we have is negating quantified statement. So if I want to negate quantified statements, right? If I'll take for all x px, then the negation of for all x is there exists x negation of px. That means I can take negation inside if and for all x gets converted into there exists x. Similarly, I can say that if I have there exists x, then it will get converted into for all x and negative negation gets inside. Okay, that is basically our negating quantified statement. Okay, so this is another example. It says that what is a logical translation of the following statement? It's the statement is none of my friend are perfect. So the statement here is none of my friend are perfect. So that means there does not exist any friend who is perfect, right? So please tell me which one of the option is a translation, is the logical translation of the given statement, none of my friend are perfect. And before moving on guys, like the session and subscribe to our YouTube channel if you haven't subscribed us. Okay, so if I'll say that none of my friend are perfect, that means there does not exist any friend who is perfect. So, because if you will remember the last option which we have corrected, some rationals, some real are rational. So we have written there exists x such that real and rational. So we want to negate that statement. I'll simply apply negation. So none of my friend are perfect. So that means there does not exist any friend who is perfect. So option D is the correct option here, right? Option D is the correct answer because if I'll say that there exists some friends who are perfect, that will be there exists x, fx and px. But here the condition is none of my friend are perfect. There does not exist any friend. So just we have to negate the statement. So here option D is correct. Just let me know guys if you have any confusion in this. Okay, so let's move forward. Next thing is nested quantifier because there may be a possibility that we'll have two variable in a statement. We have two predicate logic and we call them as a nested quantifier. So if we use two quantifiers in a same statement, that is nested quantifier. So we have here for all x there exists y, x plus y is equals to 0. This is basically nested quantifier. So if we use one or more quantifiers in a statement, that will become nested quantifier. Okay. And different combination of nested quantifier are like this. For all x, for all y. For all x, there exists y. There exists x. For all y, there exists x. There exists y. And if I have to change the places of these statements, I can write it as for all y, for all x, qxy. But in the second statement, when quantifiers are distinct, I cannot write it as there exists y for all x. That would not be logically equivalent. I cannot write it as, I cannot change the order of distinct quantifiers, right? If they are same. then it doesn't matter. I can write, I can change for this, but I cannot change for these two, right? The relative order in which the quantifiers are placed is important unless all the quantifiers are of same kind. That is, all are universal quantifiers or all are existential quantifiers. Okay, so let's move forward. If I have to take negation of nested quantifier, I'll take negation of quantifiers one by one and take the negation inside. Like if we have this statement, for all x there exists y, for all x gets converted into there exists x, there exists y gets converted into for all y, and we'll have negation of pxy. Right? Any confusion in this? So this is one example. You can check this out if you have confusion regarding negation of nested quantifier. Okay, so this is one of the questions from GATE CS 2010. It says that suppose the predicate fxy is used to represent the person that x can fool person y at time t. We have to find out the best meaning of the given formula. Right? We have given one formula. So if I'll take the negation inside, let's take this negation inside, outside, I'll have negation. There exists x for all y, for all t, fxyt. Right? So that means no one can fool everyone all the time, right? Because negation is only happening with there exist right now, right? If I'll take inside, then it will get change all the quantifiers. But at this time, uh, it's happening with only x. So I can say that option B is correct. No one can fool everyone all the time, right? Okay. So guys, that's all in propositional logic. We are going to continue with graph theory. So guys, stay with me so that you can revise all the topics in graph theory, because graph theory is very important for any competitive exam. And if you will see GATE 2022 examination, there are lots of questions regarding from graph theory. Okay, so let's move forward. So for graph theory, it says that a graph G is equals to V comma E consists of V, a non-empty set of vertices, and E, a set of edges, right? If we have set of vertices and set of edges, I'll form a graph G. And I can take this an example. This is an edge, AB is an edge, A, B, C, D, E, F are the vertices, or I'll say nodes. And if I take the line joining between them, AB, BC, AC, these are the edges. Okay, and if I'll talk about characteristic of a graph, adjacent node. Adjacent node means like B and C are adjacent to each other, so they are adjacent node, right? So adjacent nodes are the nodes if there exists an edge between them, right? So can you tell me A and C are adjacent or not? Yeah, A and C are adjacent because if you will see, there exists an edge between them. Right? There is one more path where I can move from A to B and B to C, but there exists a path from A to C, so I can say that A is adjacent to C. Next thing is degree of a node, number of edges incident from a vertex except the self loop. Self loop, because there in some cases we have a self loop like this and we do not have to consider this. So that will be the degree of our vertex. If I'll talk about degree of a vertex C, what would be the degree of a vertex C? That would be 4. Right? Okay, so let's move forward. Next thing we have is handshaking lemma. Handshaking lemma is basically a consequence of degree sum formula. So it is basically sum of degree of all vertices is equals to twice the number of edges. That is very important because it will be helpful to solve most of the question regarding degree and edges, right? So if we have one here we have one question from GATE IT 2004. It says that what is the number of vertices in an undirected graph with 27 edges, 6 vertices of degree 2, 3 vertices of degree 4, and remaining of degree 3. Right, so we have to find out the number of vertices. So tell me guys, what would be the number of vertices? Just tell me using handshaking lemma. Okay, so if I'll say that we have 27 edges and we have discussed that sum of degree of all the vertices is equals to twice the number of edges. So we have 6 vertices of degree 2, right? 6 into 2, 3 vertices of degree 4 and remaining of degree 3. Let's take x vertices of degree 3. So that are 27 into 2, right? Twice the number of edges. So solve this. 6 2 are 12, 3 4 are 12, 24. 54 minus 24, that will give me 30. 3x is equals to 30, x is equals to 10. So remaining vertices are 10, but they just don't get confused and take the option A as a correct answer. No, they have asked for number of vertices in an undirected graph. So we have 6 vertices of degree 2, 3 vertices of degree 3 and 10 vertices of degree 4. So that means 6 plus 3 plus 10. So I'll get 19 vertices in total. So here option D is correct. Right? Do anybody have any confusion in this question? Right? Because that is a very easy question from graph theory. We are going to get there will be difficulty increases as we move forward. Okay, so let's move forward. I hope there will be no confusion at any time. If you face any doubt, you can ask me in the chat section. Okay, so that is answer. Okay, so now we have some special simple graph. First is complete graph. So complete graph is a graph in which every vertex is connected with remaining n minus 1 vertices. Right, so this is k2, k3, k4, and if I'll talk about total number of edges, that would be n into n minus 1 by 2 with n vertices in a complete graph. The next graph is connected graph. A graph is connected when there is a path between every pair of vertices. So if I'll pick any two vertices and if I'll get a path from one vertex to another, I'll say that the graph is connected. So this is a connected graph. I'll find out the graph. And but if I have a graph like this, right? This is a graph, right? This is a graph here. I cannot move from this vertex to this vertex here, right? There is no path from this vertex to this vertex, so I can say that the graph is disconnected. This graph is disconnected, right? This is disconnected, but if there is a path from one vertex to another, that would be connected. Okay, the next graph is cycle. Cycle are simple graph with vertices n greater than 3 and edges 1, 2, 2, 3 up to n1. So that is a cycle C3 simply, and cycle C4. This is cycle C4, cycle C5. I can simply take n vertices and denote with each other, or I'll say that in a cycle every vertex has degree 2, right? Okay. Next thing is bipartite graph. Bipartite graph is very important. In this bipartite graph, we just have to divide our two graphs in our set into our set of vertices into two set of vertices v1 and v2, or I'll say u and v, so that if I'll take any vertex from v1, I'll get a vertex from V2, right? That is V1 is V1 is adjacent to any another vertices in V2. And if I'll take any vertices from V2, I'll get a vertices which is adjacent in V1. And their intersection of those two sets is phi, and their union is the complete set of vertices. Right? That is basically a definition of bipartite graph, and we have a complete bipartite graph if I'll connect all the vertices, if all the vertices in set V1 is adjacent to all the vertices in the set V2. Similarly, in set V2, all the vertices are connected with, are adjacent with in the set V1. I'll say that that is a complete bipartite graph, KMN. And we denote complete bipartite graph as KMN. Right. The next thing is we have one question. It says that maximum number of edges in a bipartite graph on 12 vertices is. So maximum number of edges. So I have to divide this set of vertices into two parts such that I'll get the graph as a bipartite graph. So if I'll take 4 into 1 and 6 into 1, right? There may be a possibly, sorry, and 8 into 1, another one, right? let's take from the starting. There may be a possibility that 1 in another one set, and in the second set it will be 11, 2 10, right? And 3 7, sorry, 3 9. And the next thing is 4 and 8, right? 5 and 7, again 6 and 6, again 7 and 5. Now it starts getting repeated. So if I'll say number of edges, 11 into 1 11, 2 into 10 20, 3 into 9 27, 4 into 8 32, 5 into 7 35, and 6 into 6 36. Now it will get repeated 35 32 and like this. So I can see that I am getting maximum number of edges 36, and in the case where 6 we have in one set 6 vertices, and in another set it is 6 vertices. So here option A is correct, right? Option A is correct. Okay, just let me know in the chat section if anybody have any confusion in this question, how to find maximum number of edges. So basically in bipartite graph, we have to divide set of vertices in two parts, right? And we have done that. And we have taken the a number of edges in which we get maximum number of edges, right? So we have different types of walk. So guys, tell me if it is getting too much fast, right? Just tell me, because I am taking it fast because we have to revise complete graph theory in today's lecture. If you want to go it slow, you can tell me, I'll move slow. Okay, so we have walk. A walk is a sequence of vertices and edges of a graph. Basically, if we have to move from one vertex to another, we use a walk, right? We have a open in this number of edges, or any edges and any vertex can be repeated as many times as we want. Open walk, if initial and terminal vertex are distinct, then it is an open walk, and if they are same, then it is a closed walk, right? Okay, now we have special types of walk. Trail is an open walk in which no edge is repeated. So you have to remember, if we are talking about trail, then edge should not be repeated. Vertex may be repeated, but edge should not be repeated. In circuit, not an edge is repeated, but vertex is repeated. So basically, circuit is a closed trail, right? We have initial and final vertex should be same in a circuit. So if I have to talk about circuit, I can say that it is a closed trail. For a path, neither vertices nor edges are repeated, right? Neither vertices nor edges are repeated in a path, and initial and final vertex should be distinct. For a cycle, neither edges nor vertices should be repeated, and initial and final vertices should be same. So you just have to remember all these things in this pattern, so that you don't get confused at the time of exam. Okay, the next thing we have is tree. Tree is a connected graph which has no cycles, right? A tree with n greater than equal to 1 has exactly n minus 1 edges. So if I'll see here, if I'll pick any of the vertices, it is connected with another vertices, but it has no cycle. I can check that. And basically forest is a combination of trees. If I'll take number of trees, I'll get a forest, right? Isomorphic graphs. Now next definition we have is of isomorphic graphs. If we have two graphs g1 and g2, if I'll have one bijective function which assigns set of vertices v1 to set of vertices v2, and in such a way, if a and b are adjacent in v1, then f of a and f of b should be adjacent in v2, right? This is okay, this definition is fine, but if we solve problem, we are not going to find the bijective function so simply. So we have some points which we are going to remember to check that the the graphs are isomorphic or not. So first we have to check that they have equal number of vertices. Second thing, we have to check that equal number of edges. Third thing, we have to check that they have same degree sequence. And the fourth thing, we have to check that same number of circuit of particular length. So if I'll take one example, so just remember 4 points. So if I'll take G and G dash, if I'll see same number of vertices, I'll get same number of vertices, same number of edges, and same degree sequence. But if I'll find out circuit, if I'll take circuit of a particular length, circuit or cycle of a particular length, if I'll see here in G dash, there is a cycle of length 3, but in G, there is no cycle of length 3. So that means they are not isomorphic, right? They are not isomorphic. So by these points, I can simply check that the graphs are isomorphic or not. We are not going to remember the definition to solve the questions. Okay, let me know if anybody have any confusion in this. Okay, so let's move forward. Okay, it says that connected graph. I told you before that what is a connected graph? An undirected graph is said to be connected if there is a path between every pair of distinct vertices of the graph. Right? If I'll move from one vertex to another and if I'll get a path, then it is a connected graph. Otherwise, it is a disconnected graph. Right? Okay. So let's move forward. Subgraph. If I'll take any smaller part of a graph, I'll say that it is a subgraph. G1 is a subgraph because I have taken V2, V3, V4, this part, right? This part. So I get a subgraph. Similarly, G2 is a subgraph, G3 is a subgraph, G4 is a subgraph. So these are the subgraphs. Just let me know, guys, if you have any confusion. And before moving on, like the session. Just let me know, guys, if you have any confusion in this. Okay, so let's move forward. Okay, so next thing we have is a connected component. Connected component of a graph G is connected subgraph of G. Okay, that is not a proper subgraph of another connected graph of subgraph of G. So if I'll say that this graph G1 is connected itself. So there is no this graph G1 is itself a connected component. What is a connected component? Proper subgraph that is connected, right? So G1 is connected. But if I'll talk about G2, so in G2, this is a connected component and this part is connected component and this part is also connected component, right? We have three connected components in a graph G2, right? Next thing is cut set. So in a connected graph, right, guys, just focused from here because we are going to discuss some definition which are interlinked with each other and that will be helpful in the exam. So it says that in a connected graph G, a cut set is a set of edges which when removed from G leaves G disconnected, provided there is no proper subset of these edges disconnect G. So we have to take a cut set as a set in which we have minimum number of edges because if I'll remove any of the edges, it does not disconnect G, right? So if I'll see here, if I'll take E7, if I'll take E7 outside, then it will get disconnected because one part is this whole graph and another is this vertex V6. Vertex V6 is isolated, that means it is disconnected, right? The graph is disconnected, so here cut set is E7. Simply we can find out cut set for any of the graph, right? Let's suppose if I'll see this graph, if I'll remove the vertex C, if I'll remove the vertex C, that will give me the graph G1 disconnected. And in G2, I do not have to take any of the cut set because G2 is itself disconnected, right? So the next thing is edge connectivity, minimum number of edges whose deletion from a graph disconnects G. So if I'll say in this graph, minimum number of edges. So in this we have required one edge, right? And in this we have required one edge which is CF, one edge, and in this we have required zero edges to get the graph disconnected. So I can say that uh, so edge connectivity of a disconnected graph is zero. So just remember, edge connectivity is what? If I have to remove, that means for edge connectivity we have to remove minimum number of edges, that will, so that I'll get a graph disconnected, right? Okay, the next thing is vertex connectivity. Again, same thing. We have discussed edge connectivity. We have removed minimum number of edges. We are working on vertex connectivity. We have to remove minimum number of vertices, right? So minimum number of vertices whose removal makes G either disconnected or reduces G into a trivial graph. Let's see this definition. So if I'll talk about in this graph, if I'll remove these two vertices, I'll get the graph disconnected because removing one vertex is not sufficient here, right? You can simply check that if I'll remove AB and if I'll remove AB, then I'll get the graph disconnected. So vertex connectivity for this graph is 2. And for this graph, if I'll remove this vertex, I'll not get graph disconnected. If I'll remove this vertex again, I again not get graph disconnected. And if I'll remove again this vertex, right? I have removed 3 vertex. I get a trivial graph. So that means the vertex connectivity for this graph is 3. Right? I have to remove all the 3 vertices to get a graph disconnected or a trivial graph, right? Okay, so the next definition is Euler path. So basically, Euler path is a path that uses every edge of a graph exactly once. If I am able to trace the path such that I'll move on the on every edge exactly once, then I'll get a Euler path. And Euler circuits are those whose starting point and ending point are same. So basically, you just do not have to draw every time the graph and check that the graph has Euler path or not. We have some theorems which are going to be helpful to check that graphs are Euler paths or Euler circuits. Right? We'll discuss this later, but before that, let's discuss Hamiltonian path. So basically, Hamiltonian path is a path in which we trace every vertex exactly once. Right? Hamiltonian circuit, ending vertex and starting initial vertex and last vertex should be same, final vertex should be same. So if I talk about G1, let's start moving from A, B, C and D and E and A. I have covered all the vertices and initial and final vertices are same. So that is a Hamiltonian circuit. If I talk about G2, I'll start moving from A, B, C and D. I have covered all the vertices, but I do not I haven't reached to the final point, initial point. So that means it has a Hamiltonian path. It does not have a Hamiltonian circuit, but it have a Hamiltonian path. And if I'll talk about in G3, let's start moving from A, B, C and D, right? I do not move to E. So that means G3 has neither Hamiltonian circuit nor Hamiltonian path. So we have some theorems. So just remember, if connected multigraph with at least 2 vertices has Euler circuit if and only if each vertices has an even degree. So for Euler circuit, just remember we have to check that all the vertices should be of even degree. And for Euler path, there if it has exactly 2 vertices of odd degree and other vertices of even degree, I'll get a Euler path but not an Euler circuit, right? Okay, so I can see here G1 has Euler path, but G2 has Euler circuit, because I can see that G1 has 2 vertices of odd degree, right? And this can only happen in Euler path, not in Euler. Okay, and similarly we have Dirac's theorem which help us to find out that graph has Hamiltonian circuit or not. If G is a simple graph with vertices n greater than equal to 3 such that degree of every vertex in G is at least n by 2, then G has Hamiltonian circuit. So if we have and this is not an if and only if condition, right? It's only one way. So if degree of every vertex is at least n by 2, I'll say that it has a Hamiltonian circuit. But I cannot say that if it does not have at least degree n by 2, it is not a Hamiltonian circuit, right? Similarly, we have Orb's theorem. This is also helpful. If we take a sum of degrees of adjacent vertices, it is greater than equal to n for every two adjacent vertices, then it is a Hamiltonian circuit, right? Okay. Next topic we have is of planarity. A graph is said to be planar if it can be drawn on a plane without any edges crossing. If I can draw a planar graph, I can draw a graph in which no two edges are crossing. I'll say that the graph is planar, right? Because if I'll see here K4 in this two edges, this edge and these two edges are crossing each other. So that means it should not be planar, but I can find out the planar representation of this graph. So that's why this graph is planar. I can draw this graph like this, or else I can draw this graph like this. So these two are the planar representation of this graph. So the graph is planar. K4 is planar. Regions in planar graph. So inside regions, these are R1, R2, R3, R4, R5. These are finite regions, and R6 are infinite regions. Right? Why are we considering this region? Because we have one formula which relates vertices, edges, and regions, and we can find out vertices if we have edges and regions are given. Right, we have this formula. It says that n minus e plus r is equals to 2. If G is a connected simple planar graph, n vertices, e edges, and r regions. So we have this formula. So suppose if we have one example, it says that number of region in a connected planar simple graph with 20 vertices, n is equals to 20 vertices, degree 3. So edges कितनी हो जाएंगी? 20 into 3 by 2. That means 30. I can find out the regions. So that will be 20 minus 30 plus r is equals to 2. So I'll get regions 12. Right. So there will be 12 regions. Right. The next thing is graph coloring. Right. That is also an important topic. Graph coloring. Right. It says that a coloring of simple graph is the assignment of a color to each vertex such that no two vertices are assigned the same color. No two adjacent vertices are assigned the same color, and distinct number of colors are required. That is our chromatic number. If I'll see in this example, I can assign one here. So I cannot assign same one color to here. So I have to use second color. Similarly, I can use one here, two here, one here, two here. So only two colors are required to color the vertices such that no two adjacent vertices are of same color. So chromatic number for this graph is 2, right? Independent set, right? That is important. I am saying to you that topics are interlinked, right? Now I'll discuss 4 topics that are interlinked with each other, and so listen these topics carefully. So a set of vertices I is called independent if no two vertices in set I are adjacent to each other, right? So that means I'll have to take independent vertices, right? So and the maximum number of vertices in that set is called independence number. So if I'll see this, if I'll take 2 and 4, that is an independent set, 2 comma 4. But if I'll take 1 comma 2 comma 4, that is not an independent set, right? So for above given graph, these are the independent set. But for independence number, we have to take maximum number of elements in the set. So that will be I6. I6 or I5 are the maximum number of maximum independent set, and maximum independence number is 2, right? Maximum number of non-adjacent vertices, that is independence number alpha naught g is equals to 2. Now the next thing is vertex covering. A set of vertices which can cover all the edges of a graph is called vertex cover of G. And so we have to take set of vertices which can cover all the edges. So if I'll take this example, that means if I'll take this one vertex, it's covering this edge and this edge. Similarly, this vertex is covering this edge and this edge. So 1 and 3 forms a vertex cover. But if I'll say vertex covering number, that would be minimum of the set. So I'll get vertex cover number 2. The most important relation is here is I is an independent set in G, then Vg minus E, set of vertices minus I is vertex cover of G, right? So alpha naught G plus beta naught G is equals to, and that's why I told you that this is important, because there is a relation between these two, right? Okay, so basically just remember that independent set and vertex covering set both are interlinked, right? We have one formula for that. Similarly, we have one example that it says that we have 20 vertices, size of minimum vertex cover set is 8, maximum independent set का हमें size निकालना है. So I know that alpha naught G plus beta naught G. Here beta naught G is given to me 8 is equals to 20. So alpha naught G I'll get 12. Right? So here option A is correct. Right? I can check that. Okay, so next thing is edge covering. Now, as we have discussed vertex covering, similar pattern is edge covering. So we have to take all the edges such that all the vertices gets covered, right? So beta 1G, I'll take minimum of all the vertices, all the edges. Similarly, I can find out minimum of these edges, and that would be 2, right? If I'll take this edge D, 4 and 3 vertices get covered. If I'll take this edge A, 1 and 2 vertices gets covered, right? Okay, so the next thing is matching. Similarly, I told you that independent and vertex covering number are interlinked. Similarly, we have this edge covering number and matching are interlinked. If I'll take that G be a graph, two edges are independent if they have no common end vertex, right? I have taken two vertices are independent if they are not adjacent to each other. Similarly, two edges are independent if they have no common vertex. So I consider all the independent edges and I'll call it as a matching. So if I'll take all the possible edges in the set M such that if I'll add one more edge, it will become not matching. So that would be a maximum matching, right? Okay, so if I'll talk about maximal matchings are A, B, C, D, AD and BC. But here maximal matchings are M5 and M6, right? M5 and M6 are maximal matching. And so the cardinality of maximal matching set is alpha 1G, and that is our maximum number of non-adjacent edges, right? And uh, we have one formula which says that alpha 1G plus beta 1G is equals to n, right? Beta 1G is what? Alpha 1G is our matching number and beta 1G is our edge covering number, right? Okay, complete matching. Matching of a graph G is complete if it contains all of G's vertices, right? Again, if I'll consider all the vertices in such a way that it takes all the it covers all the G's vertices, that will be a complete matching, or I'll say perfect matching, right? Okay. So we have this formula that alpha 1G is E plus beta 1G is equals to n, right? Okay guys, so that's all from my side. If you want set theory revision combinatorics, just tell me in the chat section before your exam. I'll get you revised with those topics and we'll continue in that lecture. Okay, just let me know guys if you want that lecture, because I know that set theory students are comfortable. In these topics students are comfortable. If you want it, just let me know in the chat section. Okay, so that's all from my side, and if you have any doubt in this lecture, from this lecture, you can post that in the chat section. I'll answer.